Hello, everybody, and welcome to today's webinar, which is all about security hardening of a Yocto distro. I am Georgie, and I am the head of marketing and partnerships for Witekio. So welcome, welcome, welcome. Thank you for joining. If you're joining us directly on StreamYard, hi, you can answer and ask questions in the chat that should be on the side here. If you're joining us on LinkedIn or on YouTube, then please do still ask questions. I've got my phone here to be able to look and see. And at the very end, we will be doing a live Q&A. So ask now and we can answer at the end. I'm just going to run over the agenda very quickly and then introduce our excellent speakers who will take over. So essentially, we are going to be covering on Witekio's end the 5 phases of cybersecurity and their relevance to Yocto distributions, and then talking a bit more about Yocto and how, as a platform, it can be impacted by each phase of security. Witekio is taking the first part and going into kind of top tips, as well as an overview of security as a concept within Yocto. And then Mender and Joseph is going to take over at the end and talk about the scary stuff, what to do when things go wrong, or maybe not so scary. You're going to have to listen to find out. So yes, with that, I'm going to hand over to our speakers, and then I will see you at the end, and we'll be speaking to you online as you ask your questions. So thank you. Joseph, do you want to introduce yourself first?
Yeah, sure. Thanks, Georgie, for opening up. And yeah, I'll try to be not scary. I'm actually a pretty nice guy, which actually fits my role. I'm serving as head of developer relations for Mender, which is an OTA solutions provider. And in this role, this is already my 5th instantiation of this wonderful webinar series together with Georgie.
Okay. I think that's me. So I'm Aurélien Martin. I'm an embedded software engineer for Witekio, some experience, particularly with Yocto integration, and securing embedded software, so microcontrollers, etc.
And I'm Julien Bernet, I'm security manager at Witekio. So actually, I'm the one with the scary stuff in the first place. So I'm the one coming with the problems where Aurélien and Joseph will have solutions. So I will start speaking actually. So where to start in order to have a secure product? Since your product is running on Linux, then essentially at its core, it's an application that has been contributed by you as developer, and the application provides the main functionality of the product. This application is relying on several other software components, third-party software and libraries, in order to provide this functionality. We're on a Linux system, so also the application will run besides other processes that are essential in order to maintain its proper behavior and the behavior of the Linux system. All these processes rely on the system's functionality in terms of user management, in terms of file system access, and also to provide access to the communication stack in order to provide connectivity with the network. These main functions are provided by several stacked layers of software, and at the bottom layer we'll find the device drivers, which actually provide access to the underlying hardware, Wi-Fi hardware, Bluetooth hardware, Ethernet, etc. For connectivity. It provides access to memory and provides also memory management functionalities. It provides access to the actual hardware that's involved in the human-to-machine interface, and so on and so forth. All these levels of software are gathered into the Linux kernel. So this is a massive piece of software which gathers all these several software components, and that has its own vulnerabilities. The Linux kernel itself is launched at some point by the bootloader. So if we want to speak about security on a Linux system, we need to speak about security of each of these components. Your application may be vulnerable because it has a flaw somewhere in its development, for instance, that could be exploited by an attacker. But the flaw may be in many other places, maybe in one of the libraries you are using. Maybe it's somewhere down there in the kernel and it may be triggered by your application or by another process. Maybe the flaw was in the instantiation of the Linux kernel by the bootloader. So we need to think in terms of the global system. Fortunately, under Linux, we've got, well, a variety of security mechanisms that are already there, that have been developed, that are mature. And as we'll see, possibly there are too many. So usually speaking about security will reason in terms of confidentiality of critical data and services, in terms of integrity of these data and services, in terms of access control, the ability to be able to restrict access to some data or some services only to specific entities or actors, and also in terms of monitoring, so being able to know what's going on in the system and to know whenever an attack is going on. In terms of confidentiality, for instance, we may look at what we have in terms of encryption of data at rest, so storage encryption. For instance, you may use LUKS and decrypt in order to encrypt a block device. You've got an alternative with FSCrypt. You may also use eCryptFS at the file system level. You may use software like EncFS. In terms of memory encryption, now, if we look at encrypting the random access memory, usually you will have founder-specific pieces of software. Looking at integrity, for instance, well, the main component for integrity is obviously the secure boot. The secure boot chain goes beyond only just checking the integrity of the bootloader. We may make use of systems like DMVerity, for instance, to ensure integrity of a whole partition on your system. Other software exists like Tripwire, for instance, to do runtime integrity check while the system is running. In terms of access control, well, mandatory access control indeed can be provided by a framework like SC Linux. You have the choice also, you may decide to use AppArmor instead of SC Linux, or maybe also in mandatory access control, you may make use of a lightweight framework like SMAC, and I'm not even talking about conditional access control. In terms of monitoring, you've got ODD, you've got eBPF, you've got iNotify, you've got many options. And again, the initial questions was where to start. And I fear that all of these mechanisms are fine, but do not bring an answer to where do I start in order to provide security for my application. And that's not even considering the fact that your product needs to be secure when it's first built, and then it needs to be secure all along its life cycle. So we need to try to get another angle in order to have an answer to this question. So what we could do instead of looking at what's available in terms of solution is check what are the requirements from the regulations. And let's take an example. Let's take the upcoming European Cyber Resilience Act. What do we have in terms of requirements regarding security? So that's ongoing work. So we don't have a lot that's 100% sure, but still we may find some leads here and some clues. The CRA, Cyber Resilience Act, essentially imposes requirements on manufacturers in four categories. One of them is that the manufacturers need to have a proper security risk assessment for their products. They need to apply security by design and by default in the development of the product. They need to provide security updates for their product all along their lifetime. And they also need to report security incidents on their product all along their lifetime. Let's focus on the security by design. That's a big word, and let's try to think about what it tells us in terms of development security on a Linux system. So the CRA basically categorizes product in terms of critical versus non-critical. So non-critical is the default category. Critical is split into two subcategories, class 1 or class 2, depending on their criticity. Really, this categorization is really important because it will tell manufacturer whether they can deal with a self-assessment or they need to have a third-party assessment for their product. But beyond this, we could say that the essential criteria for being secure are really the same. So the first one is have a risk assessment. You do not provide generic security. You need to be aware for each product what are the threats and how they are dealt with by the product. And the four other really can be categorized into four axes: protection, detection, mitigation, remediation. So let's go a bit more into details. Protecting a product is preventing the occurrence of attacks. So we are trying to avoid the possibility for an attacker to actually achieve one attack. What we need in terms of protection is, well, basically the risk assessment. We need a list of threats. We need to qualify which threats are realistic on the product with the right attack model. And for each threat, we need to spend some time exploring what are the relevant attack paths, how this threat could be implemented by an attacker. Once we have this, we can take the following actions. We can protect confidentiality, and we will rely on encryption and authentication processes and mechanisms in order to ensure this. We will need to protect integrity, so we will use cryptographic checksums and signatures in order to ensure that the sensitive data cannot be modified by an unauthorized agent. We will need to define processes for keys and secrets management, because since we talk about encryption, signatures, we will talk about cryptographic assets and keys, and we will need to know how they are generated, how they are protected, and how they are decommissioned when not in use. And beyond this, we need to protect against arbitrary code execution, because if an attacker is able to execute its own code on our product, then the game is over, basically. So we need some level of software hardening. The second axis is detection. Protection, 100% protection is somehow unrealistic. We will stop our efforts at some point, and new attacks will happen every day. So we want to be able to know whenever an attack is occurring or whenever an attack has occurred. If we want to know this, then we need to define what are the security-related events, and we need to have the proper technical mechanisms that will provide us with all the security-related events. We need to ensure that security-related events are logged. We need to prevent the attacker from tampering with the logs and possibly, basically wiping the markers of what has been done in terms of attacks. We need to ensure that the logs are always available at the right places. There's no use in having a log deep in the device if no one can check this. So it needs to be uploaded somehow. It needs to be analyzed on a regular way, on a reactive way. And we need to have plans for remediation in case of an attack. So we'll come to this a bit later. In terms of mitigation, now we're speaking about limiting the impacts of a successful attack. Regardless of whether an attack occurred and was detected or not, we want to be in a defense in-depth mind and assume that attacks are possible. In which case, what we will try to do is try to limit the impacts of the attack and limit their capabilities of propagating to the whole system. Here, isolation is the key word. We want to use a sandboxing approach in order to prevent an attack to propagate to all components of the product. We want to have sound permissions and access rights, unprivileged users, containers possibly, and sometimes we may want to rely on hardware-based isolation as well. The last axis is remediation. So of course, remediation means that you know that some attack is possible or some attack happened. So you can rely on detection, and also you need to be able to monitor new vulnerabilities on your product because the state of the art of attacks is constantly evolving. So in order to do this, the keystone for everything is to know precisely what's in the product. So you need a proper software bill of material of all software components that are included into your Linux system in order to be able to inventory the vulnerabilities that appear on the field on the specific components that you are using. And the second key element, obviously, is to have a foolproof way of updating the software. Whenever a vulnerability is detected, you need to be able to patch it, fix it, provide security updates. And you need to make these updates in a secure way, because nothing's more interesting to an attacker than a flawed update mechanism that would allow the attacker to inject its own malicious software. So the update process itself will be secure. And I guess Mender will talk about this a bit later. Joseph will basically manage this whole remediation topic. So these are 4 axes. We'll see in a minute with Aurélien how do we do this on Yocto Linux. Just before this, I just want to say a few words about platform security versus product security. Because as I mentioned earlier, your product is really your application running on a complete system. At some point, we may have hardened the system, but the vulnerabilities can be anywhere. Say, for instance, you've got a common vulnerability in your kernel. Your problem may be that your application allows an attacker to make use of this vulnerability to compromise the whole product. It means that at some point, there is an interface of your application that has the capability of triggering the right function in the kernel in the right way to obtain the desired effect using this vulnerability. So here the fix is easy. In some way, you just have to patch your application code and forbid this from happening. Now, since we are using a complete operating system, we may want to deal with vulnerabilities regardless of the application that will run on it. So this is called platform security. In which case, well, the landscape is a bit different and the attack surface is completely different. Because now, if you want to secure a whole Linux system as opposed to securing a product running on a Linux system, you will need to deal with every possible interface that's available to an attacker. And that includes system software, running processes, etc. And for instance, it's not sufficient to just forbid this access to this CV through your application. You will need to somehow take care with the other attack path that will use other interfaces that won't be available on your specific final product. It's much harder to do platform security, and indeed the security focus should be on the product itself. So security controls are implemented at the platform level. So the application itself cannot defend the product alone, and also we will usually want to stack up security mechanisms and have redundancy in the security approach in order to mitigate for vulnerability in one or bypass of one mechanism. But the security problem itself is not related to the Linux system as a Linux system. It's related to the Linux system as used by your application. So in my opinion, it's not possible to have a one-fits-all secure Linux platform that will work for every product. In order to secure a platform, you will have to make dire choices, implementation choices that will work with some specific product and not with another. So the solution is to provide a generic platform that is kind of hardened up to a certain level, meaning that it has recent and well-reviewed software, including software to implement security mechanisms such as encryption, access control, etc. which has robust default configuration choices in the way that if you don't touch at some specific configuration, then you should be safe. And some level of minimization and hardening while not hampering with the ability of the Linux system to run any kind of application. And maybe the most important point in this is that you need to provide a proper security documentation with your Linux system. And a security documentation is some set of guidelines that will tell an application developer how to use the product system in a secure way and how to compose really the application with the Linux system so that the end result is completely secure. Now, I will let Aurélien present you how we could do this on a Yocto system.
Thank you, Julien. Now we'll see how to put that into practice with Yocto and how Yocto can cover all of those 4 accesses. Sorry. Starting with the first one, protect. The building block, the foundation of your protection is to set up a secure boot. Unfortunately, secure boot is always, by definition, hardware specific. It can be done in or out of Yocto. What I suggest you do, sorry, yes, what I suggest you do, is to set up a class, a Yocto class, that will allow you to sign images in a reproducible manner. And that class will have to append a task to a given existing task of the recipe that will inherit it. And usually that the task you append to can be do deploy. But unfortunately for images recipes, it can be the case. So here is an example of how you would instantiate that for IMX, say. And below, you'll find a sample of how to use that to set it up for a kernel recipe, so as to sign the kernel itself and its device tree. And below again, how to set it up for an image recipe so as to sign, say, a blob of bootloader environment for your DM Verity mapping, which we'll talk more just now. So after your secure boot, you'll have to authenticate your root file system, which is a bit bigger than, say, your kernel or your device tree. And so the usual way to do that is to use DM Verity, so that's device mapping, which authenticates block by block your root file system, and the hashes of your block are hashed in turn recursively until there's only one hash at the top, which is called the root hash. And the root hash, along with other parameters, mainly offsets and sizes, will have to be passed to the kernel to inform it on how to set up the mapping. So it's well integrated in Yocto, and you need to use meta security, which is a very useful layer for security, as its name indicates, and which will bring several other features we'll mention later. You, depending on your hardware, you can need an initramfs to set up the mapping, or if your hardware, the combination of your hardware and the software allows you to authenticate random blocks of data, independent of what they are, kernel image, etc., before loading the kernel, you can do that on, say, bootloader environment blob, and put the parameters you need for the MVRT inside that environment blob, that then you can extract the data from and pass them on the command line of the kernel. And this is an example of how you would extend the standard dmverity image Yocto class to create a bootloader environment blob containing the data you need to pass to the kernel. Okay. Then once you have a secure boot to authenticate the base images and authentication of your root file systems through dmverity, you still need to have data you will act on, data who will be variable, who will change during the life of the product. And those data have to be encrypted, since you can't reliably authenticate them without exposing the key that you'll use to authenticate. So encryption can be done using a hardware secure element or some kind of TPM or hardware dependent on your microcontroller. And no matter how you do that at a low level, it will impact both your Yocto integration and your production pipeline. So here is an example of a first service that you will have to launch early at boot, and that we call below a script that will set up everything for the mapping. Here we are using dmcrypt, which is also device mapping, but to encrypt a block of data transparently. And once that script has created the mapping, you can use a line such as just below to mount the mapping as a file system where you want it. And finally, you have below a script that uses the one above, and that you will have to call at some time in your production procedure to set up the initial contents of the encrypted partition. So that's generating the keys, that's creating the mapping, that's mounting, that's creating a file system over it, and installing initial values, initial files inside the partition. Okay, so we're good with protect, and now we have to worry about detect. To detect, one standard way of auditing your what happens on your device is to use audit-d, which comes with systemd. And you can easily configure it. Here is an example of a line to add to auditd.conf that allows you to watch user modifications of the file etc password, so creation and modification of system users. And below, an example of a log of what you will get if you insert that line into audit-d's configuration. And what you have at the bottom is a log of AppArmor doing mostly the same thing. And AppArmor can be a replacement to audit-d, lighter as far as auditing is concerned, but it also it also protects, as its name suggests, as we'll see later. And then once you're auditing actively your system, you'll also have to log whatever happens in a more generic manner. Of course, logging can be handled by each program, service, recipe at its own level, but you'll have to watch how logs are stored, how they're protected, how securely they're transmitted. And there are useful settings to set to systemd journald specifically, through which you can pipe most of your logging. And those settings will make so that storage of the logs is persistent, that they are compressed, which will allow you to keep more over time, will allow you to define how the rotation is performed, how much you keep, how often you rotate your logs, etc., etc. And on the right, you have a sample of an extract of a Yocto recipe that will allow you to move your logs from the standard location to location inside the encrypted partition, so they're also protected, of course. And if all you have alongside your encrypted partition is authenticated, will allow you to write them simply. So we're done with the detect part, and we'll move to mitigate. Mitigation can be done using containers. There are several brands of containers on the market, and you know them more than me, I'm sure. What I can say is that inside Yocto, Docker is particularly well integrated inside the standard meta-virtualization layer, along with K3S on a lower level, without getting to full-fledged containers. You can use namespaces, which is a big part of how containers work. And systemd in particular allows you to exploit namespaces to isolate your services or more generally speaking, your units at less of a cost. Here you have a sample of settings that you can set on your systemd units that will allow that. The first group is to dedicate a namespace for devices, for mounts, for network, etc., to a given systemd unit. The second group allows you to make those facilities read-only for the unit, be them private or not. And then you have other useful settings which allow you to filter system calls and to bound the set of capabilities offered to your service if it doesn't execute as root. And then to mitigate further, you can use simply file permissions, which is file permissions, and discretionary access control, which is both file permissions and access control lists. I didn't put a sample here on how you could use access control lists, but simply with setfcl, you can use it directly as you would on a terminal inside your do install task, as it is done here with file permissions. So this is a static setting and nothing unusual here. But once this is done, once this is done, you can go further by using kernel security modules, KSMs, such as AppArmor, such as systemd. Systemd is a bit harsh and needs much more involvement. To set up. So I recommend as a start, if you don't have very high needs in security, to use AppArmor, which is lighter and easier to set up. So here's a sample of how you can allow some files to be read, some files to be read or written, and others to be executed. And there are quite a few settings on how a program can be executed. It can be allowed to be executed. Finally, to end with the access control, you can use user-learned permission handlers. That is, kernel security modules control system calls, how your userland programs or users can access the kernel facilities offered by the kernel, and userland permission handlers will allow system services running inside the userland to give access, to control the access they give to other services or programs. So for that, you can use dbus, which is the main way of services inside Linux to communicate between them and with the rest of the world. And here's an example of how dbus 3 can be configured to give access to a service, to an interface to a given user or group. And to go further, you can also use policy kit. What you see here isn't a policy kit configuration, it's a CPL-kit configuration, CPL-kit being a lighter implementation of policy kit we use here. It is custom tailored, and I'll encourage you to be very wary about using custom tailored security facilities in general, because those have to be checked. And fortunately, we have our very own security experts here, like Julien. So that's something we can do, but with circumspection. What it offers, what it allows us to do, is to use the control offered by policy kit, but without the overhead of having to embed the whole of Moz.js, which is the Mozilla implementation for JavaScript motor engine. Sorry. So the idea here is that you define which user or which group is allowed to perform a given action, to ask a given action with given parameters of a given service. Okay. And finally, there remains the remediate axis, of which both rescue and update will be covered by Joseph from Mender. And thank you.
Thank you very much, Aurelia and Julia. So, just like one more sentence about me, you already know, my name is Joseph, and I'm doing developer relations for Mender, which is part of the mitigations that we will cover. And I've got a very strong background in the open embedded and Yocto ecosystem, where I am running a lot of social media and also serving as community manager for Yocto. I'm really, really easy to reach out to. I'm a very friendly person. You can find my contacts there. If you have any questions concerning Mender or Yocto as a whole, feel free to ping me directly. So, what to do if things go wrong? You should have a rescue system. And why is that? There will always be something that goes wrong. It can be because of malicious actors, it can be because of bad luck, and it actually can be because of things that you need or want to do. So the first and most obvious things, obviously, is a bad actor. Bad actor might tamper with your device in a physical way. They can open it up, which you can sometimes detect if your hardware allows it. They can try to get into a terminal. They can try to manipulate the data, the applications that is on it. And as Julien already mentioned, you can detect this if your application and your file systems are signed. So, but what to do if you detect that it has if it has been tampered? And this is why you probably want a rescue system. Other things, if you want to have low-level access, for example, your service personnel, if they are in the field and you need to give them tools that are independent of the application, that will absolutely always work. For example, also if the data on the device needs to be removed, or if something happens to your hardware in terms of a bit flip on storage, things like that. In all of those cases, you will want to have at least one instance of software on the device that you can rely on. This is your rescue system. So let's look at the rescue system technically. How can it be constructed? What should you know about it? First and foremost, if you ask me, a rescue system should be one coherent binary blob that you put somewhere on the device. This is, in the most cases, a kernel plus an init RAMFS these days, because then you can directly combine them and hand off. But there are also other options like splitting it up, kernel plus init RAM disk, or if your bootloader supports it, primarily on ARM it is the case, use a fit image. A fit image is, let's say, a container format into which you can put several things and then mix and match them depending on what your hardware requires. This can be one or more kernels, one or more device trees, one or more init RAM disks, things like that. I personally will go with the kernel and init RAMFS for the rest of this presentation. What should you know about the init RAMFS? It is probably a little bit different than what you think about in terms of a root file system. Because first, I told you it should be always the same, which means it is read-only by definition, if you ask me. You should only also understand that an init RAM disk or init RAMFS that people usually construct is just meant to do some very quick things and then get out of it. So whatever you get as a template for building your init RAMFS will probably not match your requirements for init RAMFS to stay in and have useful tools. And last but not least, as we already mentioned, secure boot. This also needs to apply to your rescue system, because what fun is secure boot if you can just apply any whatever system and get into it with low-level tools? No, that's not how it's meant to be. So with that secured one thing that you can boot on your system, you also have to consider where to put it. The most obvious and straightforward choice is the boot partition, but as we all know, boot partitions are usually part of the bigger storage and therefore accessible and able to be modified in some way or the other. And you might really want to lock that down further, either by having specialized hardware. There are storage chips that you can lock down in terms of only being able to modify a partition if a specific key has been provided. You can put it into some additional storage, like a cheap QSPI that the bootloader can access, that you can make read-only in real hardware. Or if things go completely wrong, you might have a bootloader that is able to pull a rescue system from temporarily attached external storage, like a thumb drive, a USB stick, or even an SD card. Next slide, because now we're going to look a little bit on in real technology how to build an init RAMFS. Yocto gives you a lot of, let's say, scaffolding for building an init RAMFS, but it is not a finished thing. That's why I mentioned usually init RAMFS are something else earlier, because that's also what happens inside Yocto. There are templates for building your init RAMFS, but they are meant for this: do something and then get out quickly. So take this as starting points. This is not a finished solution. But in order to get the process set up, you need to set two things, basically. It is bundle init RAMFS to one, which tells Yocto, okay, now this mechanism should kick off, and you need to set the init RAMFS image, because, no, stick with that, yes. That tells the kernel which one needs to be bundled right to it. Remember, I told this needs to go into the kernel. Usually you build an image with Yocto. Now this inverts the priority, the dependency chain, because now the kernel, the finished kernel image, including the init RAMFS, depends on the root file system being constructed first. And that is the last line in here, because now if you want to get that, you have to build the kernel. Usually, if your board and BSP are properly set up, bitbake virtual kernel, and this gives you the blob, including the init RAMFS, that you can use. This is like a simple one-stop thing to get started. Now, in a real project, you don't want just the rescue system from one place. You actually want to have the whole story in one build, be it for reproducibility, be it for a license compliance, be it for whatever things, be it even just for the ease of tracing it. So the cool thing about Yocto is that you can have builds that depend on other builds. And this is what the second thing I'll want to show you today. This is multi-configs. A multi-config can say, okay, I have this build and I want to switch out a couple of things, make it a new build, and then depend on it. Look at this couple of snippets. This gives you an idea on how to set up a rescue distro. The rescue distro is meant for building the rescue system. Then you can have a recipe with an MC depends directive that says, okay, in order to build this recipe, this other multi-config build needs to be done first, and then you can pull something out of the temp directory of this multi-config build and write into your boot partition as an example. So these are the kind of like core 5 to 10 lines that you really need to know about if you want to build an additional rescue system into your Yocto build right into your boot partition. On the next slide, we still have a really short or very graphic representation of what this means. You have one build that is taken first, and then it is all like packed up and taken into the second build. So you always can reproduce this in a one invocation go. The next thing, of course, no, that's correct. So you have the rescue system, but the rescue system also will need to be updated, or needs to be able to update things, because every piece of software that you ship will eventually have to be replaced, be it for one reason or the other. And Aurelia and Julia already gave you a really good rundown of the separate components. So I'm going to be really, really quick. I'm just going to say there are a lot of things that are outside of your control. And this is the base operating system. There are people who provide support for this. There are the third-party libraries that your application depends on and that you actually buy, for example. There are the components that you maintain yourselves, and there are the hidden components, because a real-life system these days is usually not just one big processor in the center that runs all of the stuff, but it is a lot of other stuff around it. If you think about an industrial system, there are drive controllers, there are elaborate sensors, there might be even vision systems, all kinds of stuff, and all of those will need an update sooner or later. So, next slide. The key here is to have an update system that is so flexible that it can cater to all of those requirements, while at the same time providing a high level of robustness. This means that there is no one-size-fits-all flow for an update. This is one of the things where Mender really shines, because there is the A-B flow with a fallback partition that is shown here on the top layer. You use this for updating the operating system in a fail-safe way. If something goes really, really wrong, you can just roll back and have a non-brick device. But if you think about other things like your application, your assets, your drive controller, where you need to sometimes follow really complex other processes that are not just like an A/B switch back and forth story, then you need to have the flexibility of an update module where you can literally put in every flow that your project might require. Mender, how to get it into your Yocto build. This is just like a super minimal example. And why am I choosing such a minimal example when some of you might know that the board integration is actually more complex in real life? Because the integration can be so easy if you have a proper board, if you have a modern board, one that supports a good UEFI boot chain. I personally would love to see this. So I keep on like cheering UEFI on, because it really makes your maintenance life easier. And for Mender, it means you just have to say inherit Mender full, because that says, yeah, give me all of the magic, just put it inside. UEFI is a puzzle piece here. And then you just have to declare, okay, whatever falls out of this is the artifact name. I'm going to give one of it. And that's it. Essentially, you build your image again, and you have it completely menderized. That's why we say it is important to have the flexibility and to be not opinionated about it. Because if we would tell you how to create your operating system, then you would probably say, but this does not match my needs. We say, we don't care. We do over-the-air updates. And that's already my conclusion. I strongly believe that whatever you do in software, that whatever you put out there will have to deal with attackers, with vulnerabilities, with bugs, with whatever at some point in time. And for this, you need to have a strategy in order to deal with it on software or in software on the device, and how to get new software out. This is my take on it. If you need a hardened, a secure build, hopefully by Yocto, that your understanding of hardening does not end at the software selection or the configuration. Hardening means that your whole life cycle of the device really needs to be considered and needs to have the points where you can insert handling, mitigations, remediations for all of the things that will happen, especially as we are talking about things that have a long lifetime, 10 years, 15 years, maybe 20 years, or even longer. And just a short final word on this. We, with Mender, are an over-the-air update solution provider, and we are here to help you with that. With that, we hop up to the next slide. This is where you can find us. This is where you can find me. Go give it a try, hop onto the board, and I don't know how much time we have left for questions, but I'm happy to take whatever is thrown at me. Thanks for having me.
But yes, we do have time for some questions. So some have come through, which I will put up on the screen, some on LinkedIn, as well as some on here on StreamYard. But yes, thank you for sticking with us and for telling us. Okay, so the first question is from Mike. I will show it on the screen. Are there any strategies to handle systems where boot time is a concern, and also the need to have encrypted rootfs? Maybe just focus on signing critical partitions. Who would like to handle it, or has anyone got something to say about it?
Well, I have an opinion, but it's, let's say, not what people want to hear.
Oh, Joseph's opinion. Okay. All right. Does anyone from Witekio, do one of you guys want to handle it before Joseph comes in with his iron hammer approach, which we always like in the questions?
Yeah. As I mentioned when going through DM Verity, if you pass your DM Verity parameters through on the command line of the kernel rather than through booting an initramfs, a dedicated initramfs, you gain much time, and it actually doesn't cost much. Maybe depending on the kernel and the architecture, around 2 or 3 seconds of boot. At most. Yes, you should, of course, encryption costs more, and you should select what you want to encrypt. Of course, you can split your system in as many partitions as you need. So take advantage of that, yes.
Okay, Joseph, you go.
That actually was pretty close to what I was about to say, but I would just be pretty blunt about it, because I don't believe in root file system encryption. It's a checkbox for so many people, and if you ask me, then it's in 99% of cases, it's just like, it's a checkbox and it doesn't make sense. It costs time, it hinders engineering, and it's just stupid. Because why? Nobody wants to look at your glibc, and nobody wants to look at your bash binary, and really nobody wants to read your systemd units. They are completely uninteresting. What you need to care about is your application, is your company's IP, is possibly the user data, the process data, all of that. And I say, just encrypt that. make sure that the rest of your boot flow is streamlined. Be quick. Yes, signing is okay, but for encryption, be super, super picky, because encryption can backfire badly, especially if you need to rescue data.
Yeah, I can totally follow that. Actually, at Witekio, I've never seen a rootfs encrypted. We authenticate and we encrypt only the data, eventually the application, the core application with a sensitive method. Yeah, but never the rootfs.
Okay, just for completion, I concur with everything that has been said. In any case, it's really good practice to have some dedicated encrypted area where you make conscious choices of protecting this or this data. At least the guarantee, the benefit you get from this is that you don't get the events of false security you may have by considering that your whole rootfs is encrypted in the first place. So it's something we don't do.
Guys, I think everybody here has just witnessed a miracle. 3 engineers agreeing with each other. What is this? It is a happy day.
So now I'm gonna put out something really, really crazy, because a friend of mine whom I'll meet, I think tomorrow, has actually just released open source on GitHub a thing that does basically exactly what we just discussed, because it is meant to encrypt and sign the application based on a PKI backend. So whenever you actually boot up the thing and want to run it, it makes sure that you are still certified and permitted to run it, and it is untampered with. I can't find the link right ad hoc because I'm staring at the camera, but if somebody wants me to dig it up, or Georgie, if you want to put it in the log, I'll happily share the link for it.
Please do. So after this, like I said, I'll do the recording and then I'll send out the slides as well so everybody has it. We have another question which I want to get done so that everybody does get answered. Does Mender handle LXC update or Docker updates? For instance, do you think container techs for embedded systems are mature enough to get on our embedded Linux systems? Obviously, Joseph, this is for Mender.
Yes, we have an update module that is for Docker containers directly. We have an update module that is meant for more complex things like Docker Compose and Kubernetes. We do not have one that is tugging into LXC, but if you have those as blueprints, it's definitely not a lot of magic involved. It's more like doing the legwork. And if you have an interesting use case for that, ping me on LinkedIn or on the Mender Hub, and then we'll see how to figure it out. Thanks.
There we go. Nothing to add on our side? No, we're good? Just making sure. Okay. Okay, so next question. How does systemd isolation mechanisms compare to that of Docker? Any thoughts or insights? Thoughts and insights, guys.
Yeah, you run, I guess.
Okay, I think the question is for me. It's not actually the same thing, because systemd isolation mechanisms you use to isolate a service which is otherwise closely integrated into your system. When you use Docker, you isolate an image, you isolate a container, and it's a separated environment, even though it can interact with the system through network interfaces. If you don't, depending on how much you isolate everything. So use systemd isolation mechanisms for what you would otherwise put into a systemd service or a unit, more generally speaking, and Docker for doing Docker.
Okay. Next one, just to make sure we get through as many as we can before we have to log off. Regarding the rescue system, do you mean that the kernel and interim FS should be there for both of the AB partition and boot it if both of the partitions are tampered with? So then every boot partition would have 2 kernels. Would that take too much space?
No, that's not what I propose. The boot or the A and B partitions should be self-contained and disconnected from the rescue system. The rescue system should be somewhere completely else. So in a perfect world, you have 3.5 systems on your device. You have A, the active, you have B, the inactive, you have the rescue system somewhere else. If both are being tampered with or broken or whatever, and the 3.5 is a way to load a signed binary from removable media. So it is not on your system, but it can get into your system if somebody authorized really needs it. That is how I would do it, but your mileage may vary, and your use cases definitely do.
Okay. I think I'm just checking, just one last check, but I think that's everything from everybody. Again, just so you all are aware, I will send slides, I will send Joseph's link, and I will send an updated recording from our end because of the audio issues and us freezing to everybody on the call who attended or who is watching on demand. So don't panic, everything will be sent to you, I promise. Any other questions? We have one more. Does everybody have time for one more? And then we will go. That will be it. Just so that we make sure. I'm just trying to make it up to the lovely people who stayed after such a freezing on my behalf. So one last question is, how does Mender configuration add-on work? When maintaining a configuration partition, user specific, is there a way to authenticate the partition using Trust Boot? Joseph, obviously for you.
Okay, I think that was a little too much in one sentence. I'll just wait until it pops up on the big screen. Then I'll read it for 1 second, and then I'll probably say I don't know. Okay, but I'll try.
There's a lot of words.
Whoop. Okay, so yes, I'm pretty sure there is, but it is not Mender specific. If you ask me, the problem is generic. How do you sign user configuration? I don't know. So this might be like triggered by a Mender configuration change here, but having a signed user configuration storage, I don't know, but I think Aurelia and Julia probably have an idea on it.
I think we may want to have a larger discussion on this one, because I figure it would require some very specific process for a user to get its configuration authenticated somehow by some party that is able to provide signature. So it goes far. I don't know what the use case here is, and for sure I've never met it yet. But feel free to ping us, and we can check this, because there are many things involved here. I'm really concerned here about what would the signing process be, and how would trust be handled somehow along the whole chain. So feel free to come back to me by LinkedIn or by email. We can discuss this.
So what I'm hearing there is that this is a perfect case of a Mender Witekio collaboration going together, guys. This is the joy. This is why we're here. And that's exactly
It is actually more like the engineers, everybody wrecking their brains at the moment, because if you don't mind me snatching 30 more seconds, the interesting part here is that the signing would have to happen in device, because the user configuration could be different or will be different for each and every device out there. So you would have to have a kind of trust anchor on the device, but it would need to be able to re-sign or recertify the storage upon each change, and that is an interesting challenge.
Yeah, definitely, and it's interesting both technically and also from a security standpoint. Yeah, let's have a chat about this.
Sounds interesting. Okay, maybe we'll do a webinar just on that. Okay, right, that is it, guys. Thank you so much again. Sorry for the earlier technical issues. I will send everything out tomorrow. And thank you so much to all of our speakers. Thank you for holding down the bar and for being just the perfect hosts. So yes, have a lovely evening, everyone. Thank you again for joining us, and we will see you on the next one. Bye, guys.
Thanks a lot. Bye.
Bye.